Okay guys, cardiac access determination using quadrant method. This is a real simple method. What you need for this one is you need the lead 1 and lead AVF. The reason for that is this, that if you draw a circle where the lead 1 will cut horizontally and lead AVF will slice it vertically. So we get four nice quadrants, and that is the point of this quadrant method, that you develop 4 quadrants and then you figure out where the axis is. Now remember this, that lead 1, when it is projected on this system, the positive end is on the right side of this and negative end is on the left side. What that means is that if the lead 1, let me draw the lead 1 here, let's say this is a potential in lead 1. And here, this potential is positive. How do you know that? I will just give you a quick hint. This point here is called the J point. J point, or joining point. This is where QRS complex joins the depolarized state. Anyways, this point is also called the 0 millivolt point. And this can be taken as a reference, and everything above is positive and everything below this point is negative millivolts. So with that keeping in mind, if you look at the QRS complex here, I'm going to make it a little bigger here. So this one is the R wave. And you can actually obviously see that this R wave is much bigger than the S wave here. However, we can also do a calculation, and how we can do that is we need to have the ECG boxes drawn here. So let me just draw a few boxes. Let's say these are the boxes, and you know that every one large box is 0.5 millivolts. So I'm going to mark that here. 0.5 millivolts plus another 0.5 plus another 0.5 and another 0.5. So this is almost 1.5 millivolt height, positive direction for the R wave. For the S wave, which is here, it almost seems like it is one box high. So that would mean 0.5 millivolts, but negative. So what you do is you sum them up, the Q and R and S wave. In this one, there is no Q wave, so you will sum up R and S wave. So sum will be R equals 1.5 millivolts positive, and S equals minus 0.5 millivolts, and when you take the sum, you'll end up with positive 1.0 millivolts. Cool. So this means you have positive side deflection. That is, you have deflection on this side of the limb lead 1. What does that mean? What that means is that the axis of the heart is going to be on this side. Remember this side, this half. The lead 1 is positive for both quadrants, upper quadrant and lower quadrant. On the other half, this side, the lead 1 is negative. As you can see here, this is the negative. So if the lead 1 is negative, it is going to fall on this half. Now let's also see AVF. So now let us see AVF. We are going to draw that in blue color. AVF is this vertical line. So AVF. Positive is down here and negative is here. What that means is that if AVF is positive, it is going to occupy this half, both quadrants. And if it is negative, it is going to be present in this upper half, any one of these quadrants. That also tells you that one lead cannot tell you what the axis is because it only brings you to a half and not to a quadrant. Okay, so let's make a lead AVF as well for our work and see if we can work with it. So let's say our AVF lead has this data. This is the situation with the AVF lead. So how do you work with it? Once again, look at the J point. This is the J point. This is where the junction of the QRS with the depolarization isoelectric line is. So this can be taken as 0 millivolt. So if now I draw a line at this level, then everything above is going to be positive and everything below is going to be negative. Here you've gotten the R wave, and the R wave in this case is, you can see visually that it is negative. But if we calculate it, let's say this is box 1, this is box 2, this is box 3, so 0.5 millivolts negative, another minus 0.5 millivolts, and let's say this is about minus 0.3 millivolts. So the total sum of the R wave here is minus 1.3 millivolts. There is no Q wave and no S wave to subtract from. So we've got a minus 1.3 millivolt. If we now go back here, if the AVF is minus, that will mean we are talking this half, right? So which quadrant out of those? We have to combine the information from these two leads to figure out which quadrant. So lead 1 is positive, lead AVF is negative, and that is lead 1 is positive here, and lead AVF is negative here. So this is the quadrant that we are talking about. So the axis is somewhere in this quadrant. Now I hope you also know that from minus 30 millivolts to plus 110 millivolts, why do I'm saying millivolts? I should say degrees. So from minus 30 degrees to 110 degrees, everything is normal. So now if this quadrant is occupied, but if the axis is in this range here, then we'll have a normal axis. But if the axis is present, in this range, then we would have left axis deviation. How do we calculate that? Easy. What we have to do is now we have to plot the vectors from these leads on the axis. So let's do that. Now what was the value on the lead 1? It was 1 millivolt. So let's say 1, 2, 3, this is the 1 millivolt. What is the value on the lead AVF? It is minus 1.3 millivolts. So let's say this is 1, this is 2, this is 3, and this is 1.3 somewhere over here. So we've gotten two vectors now. If we create their tangents, their projection, then this is the point that is for the axis. And if I go like this point seems like it is cutting this quadrant in the middle, and the quadrant is made up of 90 degrees, so in the middle will mean minus 40 degrees, 45 degrees. And of course this is not minus 30 degrees, which will be normal. So this particular ECG, this particular set says that this patient will have left axis deviation. So that is how you figure out what quadrant is responsible, and then you make it precise by actually plotting the vector. There is one more way that you can make it precise, and that is that you combine more than one way. So you use the quadrant method to figure out which quadrant you are sitting in, and then you use other leads to figure out if you are within normal range or not. And which quadrants are going to need this help? Look here, if I cut it again, minus 30 degrees to 110 degrees, this is the normal area, right? So that is quadrant, this quadrant, this quadrant, and this quadrant. Three of the quadrants would need further clarification. This quadrant here, this will not. If you see that the AVF is negative and lead 1 is negative, and the axis is falling in this quadrant, then you do not need to do further analysis because this is already not ambiguous. However, if the data falls, and similarly, if the data falls, if the lead 1 is positive and lead AVF is positive, then the axis falls in this quadrant, which is normal, definitely normal. So if it is definitely normal, you do not need to do anything. However, when you have limb lead 1, which is positive, and AVF, that is negative, that is this quadrant, or lead 1, that is negative, and AVF, that is positive, that means this axis, then you need to disambiguate. You need to calculate further to see if it is within the normal or abnormal range. So thank you very much. Hopefully this helps you understand how the quadrant method works for axis derivation.